Dear student, welcome to our official YouTube channel of Hasmukh Goswami College of Engineering. I am Professor Vrindani Vaidya, Faculty of Civil Engineering Department. Today we are going to discuss about the gravity dam under the subject of irrigation engineering. Learning objective of today's session, that is types of gravity dam, advantages and disadvantages of gravity dam, and forces acting on the gravity dam. Types of gravity dam. Now, a gravity dam is a structure so proportioned that its own weight resists the force exerted upon it. Types of the gravity dam are masonry dam and concrete dam. In the past, the gravity dams were made up of the stone masonry, but now the masonry dams are rarely constructed. A gravity dam or the concrete dam may be either straight or curved in the plan, suitable across the gorges with very steep slopes where earth dams might slip. This is the image of the gravity dam. Now, advantages of the gravity dam. Gravity dams are relatively more strong and durable than the earthen dams. It can be suitable for moderately wide valleys having steep slopes. It can be constructed to a very great height provided suitable foundations are available to bear the stresses. The fourth one, that is, it can be well adapted for the use as an overflow spillway crest. Earthen dams cannot be used as the overflow dams. Fifth one, the maintenance cost is very low, and the next advantage is it doesn't fail suddenly. Now, disadvantages of the gravity dam. So, first one, gravity dams of greater height can be constructed only on the sound rock foundation. Second one, initial cost is more than the earthen dam. Third, it takes the longer time in the construction. Fourth, it requires more skilled labor than the earthen dam. Fifth one, that is, subsequent raise is not possible in the gravity dam. Now here, forces acting on the gravity dam. Now various forces that are acting on the gravity dam, such as water pressure, then weight of the dam, uplift pressure, ice pressure, wave pressure, silt pressure, wind pressure, and earthquake forces. First, we will see about the water pressure. Now, water pressure, it is denoted as capital P, is the major external force exerted by the water stored in the reservoir on the upstream face of the dam. It can be calculated by the law of hydrostatic pressure distribution, which is triangular in the shape, right, as shown in the figure. Now there will be the two cases. Here the first case is when the upstream face is vertical. So in the figure you can see the upstream face of the gravity dam that can be vertical. Here the intensity is 0 at the water surface and it can be equal to gamma WH at the base. See here in the figure you can see it easily that water pressure at the top of the water surface, it will be 0 and it can be about gamma WH at the base, where gamma W is what, that is the unit weight of the water, and his the depth of the water as shown in the figure. Now the resultant force due to this external water pressure, that is P, that is equal to half gamma WH square, that can be acting at h by 3 from the base. See, this is the triangular in shape. So CG of the triangular that lies at 1/3 from the base. So this water pressure that can be acting at h by 3 from the base. Now second thing, that is when the upstream phase is partly vertical and partly horizontal. See, in the figure, the upstream phase is partly vertical and partly horizontal. This is the major external force acting on the dam, that is the pressure component on both the upstream and downstream side are vertical component, horizontal component, and the tail water pressure. Now here we already know the unit weight of the water, that is gamma W equal to 1000 kg per meter cube. Second force that is acting on the gravity dam, that is the weight of the dam. Now generally this is the major resisting force, and the unit length of the dam is considered. Here the cross section of the dam that may be divided into several number of triangles and rectangles, and the weight W1, W2, W3 etc. may be computed. The total weight of the W of the dam acts at the CG of the section. See here, whenever we can find the CG, we have to divide this figure. So here this gravity dam, it can be divided into three figures. There will be two triangles and one rectangle. So you can easily find out the CG of this section, and it can be exactly lies at the weight of the dam that can be exactly lies at that can be exactly act on the CG of the section. Now weight, that is equal to volume per unit length multiplied by density of the material. The third force, that is the uplift pressure. Now uplift pressure is defined as the upward pressure of the water as it flows or sips through the body of the dam or its foundation. Now here the area over which the uplift pressure acts has been the question of the investigation, and here there will be the two cases. First, the uplift pressure diagram where no drainage gallery is provided, and second one where the uplift pressure diagram when the drainage gallery is provided. So this is the uplift pressure diagram in case of the drainage gallery is provided, and in case of where there will be the no drainage gallery. Now you can easily see that when no drainage gallery is provided, see the uplift pressure at the hill, it will be gamma WH1, and uplift pressure at the toe, it will be gamma WH2. Now same way, when the drainage gallery is provided into this second figure, here the uplift pressure at the heel, it will be gamma WH, and uplift pressure at the toe, it will be gamma WH dash. Now here the drainage gallery is provided, so we have to find out the uplift pressure at the drainage gallery, and that is equal to gamma W H dash plus 1/3 in the bracket gamma WH minus gamma WH dash. Now the next force that is acting on the gravity dam, that is the pressure due to the earthquake. Now earthquake waves imparts the acceleration to the foundation under the dam and causes its movement. Now this earthquake wave may travel in any direction. So for designing purpose, horizontal and vertical direction that will be considered. Now according to IS 1893 2002, India was divided into 4 zones. Zone here second, third, 6th and 5th. So here see, in the seismic zone map of India 2002, about 59% of the land area of the India is liable to seismic hazard damage. Now zone 5, see here, it can be seen by the red color, and the intensity here for the earthquake is very high risk zone and area liable to shaking the intensity 9 and above. So on the Richter scale, if the intensity of the earthquake is 9 or more than 9, it can be considered into zone 5. Now zone 4, so it is high risk zone. Here the intensity is 8. For zone 3, it will be moderate risk and moderate risk zone, and intensity is 7. Zone 2 having the low risk zone, and here the intensity is 6 or lower. Now earthquake acceleration is usually designated as fraction of the acceleration due to the gravity. Now seismic force that can be found out with the formula mass into earthquake acceleration, and it can be expressed as alpha into g, where alpha is known as the seismic coefficient. Now seismic coefficient that is divided into two parts: horizontal seismic coefficient that is alpha h, and vertical seismic coefficient that is alpha v, that is equal to 0.75 alpha h. Now alpha h can be determined by one of the two methods. There will be two methods for finding out the seismic coefficient, horizontal seismic coefficient, that is seismic coefficient method, and second one that is the response spectrum method. Now seismic coefficient method that can be used where the dam height that will be less than 100 meter, and response spectrum method that is used where the dam height is greater than 100 meter. Now in the seismic coefficient method, as per IS 1893-1984, the horizontal seismic coefficient that can be found out by alpha h is equal to 2 alpha 0, where alpha 0 is the basic seismic coefficient, and this basic seismic coefficient as per IS 1893-1984, the seismic zone for the second, third, fourth and fifth, the basic seismic coefficient that will be 0.02, 0.04, 0.05 and 0.08 respectively. Now the second method, that is the response spectrum method. So as per IS 1893-1984, the horizontal seismic coefficient that can be found out by the formula alpha h is equal to 2 f0 SA upon g, where f0 that is the seismic factor, and here the seismic factor as per IS 1893-1984, the factors for the zone 2 it will be 0.1, for zone 3 0.2, for zone 4 it will be 0.25, and for zone 5 it is 0.40. Now the next force, that is the ice pressure. Now the ice formed on the water surface of the reservoir is subjected to expansion and contraction due to the temperature variation. Now the coefficient of thermal expansion of ice is 5 times more than that of the concrete. The dam face has to resist the force due to the expansion of ice. This force acts linearly along the length of the dam at the reservoir level. According to IS 6512 1984 recommends that 250 kN per meter square applied to the face of the dam over the anticipated area of the contact of the ice with the face of the dam. Now the next force that is acting on the dam, that is the wave pressure. Now wind blowing over the water surface in the reservoir that exerts a drag on the surface due to which ripples and waves are formed. So the impact of these waves produce the pressure on the upper portion of the dam, and the magnitude of the wave pressure mainly depends on the dimension of the waves, which in turn depends on the extent of water surface and the wind velocity. Now, as per IS 6512 1972, for determining the wave height, the Moliter's formula was used, which can be HW is equal to 0.0322 under root VF plus 0.763 minus 0.271 fourth root of F, where for F less than 32 km and for greater than 32 km the height of the wave that can be found out by the formula 0.0322 under root VF, where hw that is the height of the wave in meter, v that is the wind velocity in kilometer per hour, f that is the fetch or the straight length of the water expanse in kilometer. Now wave pressure intensity that can be found out with the formula Pw is equal to 2.4 gamma WHW, and it acts at a distance of 1 by 8 of HW above the still water surface. The pressure distribution is curvilinear, and however for the design it is assumed to be represented by a height equal to 5 by 3 of HW. Therefore the total pressure that can be given by the formula Pw that is equal to 2.4 gamma WHW into 1 by 2 of 5 by 3 of HW, that is acting at 3 by 8 height of the wave above the reservoir surface. Now the next force that is acting on the dam surface, that is the silt pressure. Now practically all the streams that carry this silt along with the water, which during the floods may be in enormous quantity. So the river brings the silt and the debris along with it. The dam is therefore subjected to the still pressure PS in addition to the water pressure. So for determining the silt pressure, the Rankine formula that can be used, and that is here PS is equal to half gamma dash H square 1 minus sin phi upon 1 plus sin phi, that is acting at H by 3 height. Here the PS is what? That is the total silt pressure, gamma dash that is the submerged unit weight of the silt, H that is the height of the silt deposit, and phi that is the angle of internal friction. Silt pressure, according to the IS 6512 1972, the silt pressure and the water pressure exist together in the submerged silt. The following are the recommendation for calculating for PSH, that is horizontal silt pressure, that is equal to 1360 kg per meter cube, and PSV, that is equal to 1925 kg per meter cube. The next force that is acting on the gravity dam, that is the wind pressure. It is the minor force acting on the dam. It acts on the superstructure of the dam, and wind pressure is required to be considered only on that portion of the dam of the structure which can be exposed to the action of the wind, that is the superstructure. So normally the wind pressure is taken as 1 to 1.5 kilonewton per meter square for the area exposed to the wind pressure. Now wind pressure is not a significant force and therefore sometimes not considered in the design of the dam. Now the last one, the combination of loading for the design. So different load combinations we have to take. So for the construction condition, load combination A, so dam completed but no water in the reservoir as well as no water on the tailwater. Then second combination, that is load combination B for normal operating condition. So normal operating condition is that full reservoir elevation means top of the gates or at the crest, and normal dry weather tailwater, normal uplift pressure, ice and silt pressure that can be calculated. The third combination, that is the load combination C for flood discharge condition. So reservoir of maximum flood pool elevation, all gates open, tailwater at the flood elevation, normal uplift pressure and silt pressure that can be calculated. Next loading combination, that is D. So combination A with earthquake, that is considered as combination D. Same way load combination E, that is combination B with earthquake but no ice pressure. Then load combination F, that is combination C but with extreme uplift pressure. And the last one, load combination G, that is combination E but with extreme uplift pressure. Thank you. If you like the content, please like, share and do not forget to subscribe our channel for more educational videos. Thank you.